Okay, here's where we were last time. We were talking about this single variable symmetry theorem, and this is kind of an afterthought in single variable calculus. It's not really, I don't know, I didn't see it very much in single variable calculus myself, but this is a theorem that generalizes very nicely to multivariable. Right. So what I want to do now is talk about how to generalize this. Remember, the big idea here is that we have an integrand that is odd, and odd means this right here, right? That sorry. Okay. An odd integrand means that the integrand has this property right here, right? So if you negate the input, you negate the output. And I'm going to give you a slightly different take on what we mean by this. I'm going to draw the x-axis. I'm going to point out that that's 0. And if you have some point x, right, then when we talk about negative x, which is here, I forgot to label my x. You can think of this as adding a minus sign. You can think of it as negating it. I'm going to give you a slightly weird take, perhaps. I'm going to think of this as reflecting through the origin. Kind of a weird way to say the same thing. But nevertheless, that's a perfectly reasonable way. You can think of the origin as kind of a little mirror. And when you're x here, you would see your image, reflection image, there at negative x. Okay. What's nice about this is that this will generalize. I seem to have gotten ahead of myself. Okay, so let's talk about why this theorem is true. We'll come back to the reflection point of view in just a second. Why is this theorem true? The big idea is because my domain is symmetric, namely from negative a to a, every term in the Riemann sum has another term that is its own reflection. Right? So every point in the interval from negative a to a, if you reflect, you get another point in the interval from negative a to a. So every term in the summation, there is a corresponding term reflected on the other side. So all the terms in the Riemann sum kind of pair up. And then because of the oddness, right, keep in mind the oddness of the function means f of negative p is negative f of p. Now that's exactly what oddness says. I can multiply on both sides by delta x. Perfectly free, perfectly legal. Having written that down, having this equation established, notice what I can interpret from that is that this, what you might call p term in the Riemann sum, that's one of the terms in my Riemann sum, and this, what you might call negative p term, that too is a term in the Riemann sum. And it says right here now that these cancel. Right? They're negatives of each other, so in the summation, they cancel. So everything cancels. Everything pairs up. Everything cancels. There's nothing left. The integral is 0. Okay, so that's the big idea. That's why this theorem is true. I hope that's reasonable intuition. Side note, if you want to prove it with a substitution, that works too. You are not responsible for this if you don't want to look at it. It's not because it's hard. It's not hard. It's very straightforward, which is short on time, and I don't have time to talk about it. But in case you're curious, while we're talking about symmetry theorems, in the section on change of variables, it's because of this argument. This is an argument that uses a substitution, which of course is a change of variables. Okay. All right, so let's generalize. Again, back to the idea of reflections. Notice we can talk about reflections over a line in R2. All right, so this is kind of what you might call the sort of the one dimension up kind of extension of the reflection idea that we talked about on just the x-axis. Okay. Now, how we write how I define this rigorously is not really the point. Reflection means exactly what you think it means, right? And in most cases, you can kind of draw the picture and see the formula for the reflection just by, there it is. We'll do a couple of examples. And we can continue the generalization. We can talk about, let me do it like this. We can talk about what it means for a function to have odd symmetry. Just like in single variable calculus, if you reflect the input, you negate the output. It's a total ripoff, right? Shameless ripoff of the idea of oddness from single variable. You can also talk about what it means to have a symmetric domain, and I'll draw a picture of one in just a second. I don't want to wing it on that because it takes time, and it's hard. Time is of the essence, etc. But what does it mean for a domain to be symmetric? It means that it is its own reflection. If you reflect the entire set, same thing, right? And this is some notation if you want to write it down formally. We don't need to worry about that either. Okay. All right, so here's the awesome theorem. Super powerful result here. If you have a double integral with an odd integrand and a symmetric domain, then your integral is 0. You don't have to integrate anything. You don't have to slice. You don't have to worry about whether your slicing is going to hit corners, and thus that you'll have multiple double iterated integrals to compute, right? And it can get, y'all have done a bunch of integrals. Y'all know they can get a little out of hand sometimes, right? You don't have to do any of that. Boom. 0. This is a really nice theorem. I love this theorem. Now, there are a couple things you got to worry about, and so let me point that out. You do have to have both conditions satisfied. This is a very common mistake that I see students make. I see this happen a lot, right? And as y'all know, when I see certain mistakes happen a lot, I like to make a big deal out of it in class and hope that'll reduce the occurrences, and I think that works. So yeah.
How do we determine if F is odd?
Yeah, I'll show you in a minute. Yep, getting there. We're going to do at least a couple, 3 examples. So very, very commonly, students will see their domain is symmetric. They'll just looking at a picture of their domain, and they're like, oh, it's clearly symmetric. And then they just think that automatically tells them the integral is 0. Well, absolutely not, right? It's one thing for the terms to pair up, as it were, but you also need them to actually cancel. To cancel, they have to be negatives of each other. Right? So you need the oddness. The oddness is essential. Don't make the mistake, please, don't make the mistake of seeing a symmetric domain and say, so cancellation 0. It's just not true. The other common mistake I see, this happens, you got to use the same line for both of the oddness and the symmetry of the domain. If you use different lines, there is no such theorem. This has got to be the same line for both. All right, so I'm going to show you an example of that as well. Okay, why is this true? Well, again, we've kind of already made the argument. There's a change of variables point of view. Again, if we had an extra hour per week, I would totally show you this, but we don't, and so I'm not. And you don't have to worry about it if you don't want to, but this is actually a pretty cool, clever example of a change of variables. We're just literally using the reflection itself as the change of variables function, and if you want to read through and follow the detail, go ahead, but you don't have to. What I think is actually pretty satisfying, and I think worth taking a moment, is this Riemann sum point of view. It's just a 2-dimensional version of the Riemann argument that we made previously. Because our domain is symmetric, interpret liberally for my drawing there as best I could do. Because of the symmetry, anytime you look at any term in the Riemann sum, there is a reflected term in the Riemann summation that it's going to pair up with. And then, because of the oddness, Remember, oddness tells us that when you reflect the input, you negate the output. And that means that when you look at these two terms, let's see here, that term in the Riemann sum is that. This term in the Riemann sum like that. And they are, apparently, because of the oddness, they are negatives of each other. So in the summation, they cancel. So very, very similar to the argument we made in single variable. The single variable version of the theorem, it just adapts it to the multivariable, to the two-dimensional case. Okay. Example. Let's see this in action. This is a really inconvenient integral. Now, I don't think I need to sell very hard in trying to persuade you that this is an inconvenient integral, right? And here's the thing. It's actually quite a bit worse than you probably think it is at a casual glance. You may think that the problem is going to be that you're going to have to integrate, this thing, right? Well, but y'all have seen this before. I won't go through the details because we're going to find a much more efficient solution in a second. But the algebra for your bounding curves gets into your inner bounds, which gets into your outer integrand, which means all of this quartic stuff is going to work its way into here also. This is a horrendous integral, possibly not even tractable. If you do it by, the usual method, chop it up, iterated intervals. Okay. So how are we going to solve this? Let's draw a picture of the domain. Again, usually our first step. And let's see, I'm going to draw the rough picture here. So x, y. And let's look at this curve. That looks approximately like this, and I'm going to appeal to y'all's memory of high school algebra and maybe single variable calculus, something like that. And it looks about like this. Is that familiar? I hope you all remember enough of that material that you can persuade yourself it looks approximately like this. And let's see here, this curve right here, that's an easy one, y equals -1. That'll be something like that. And we are interested apparently in the region, wrong color. We're interested in the region bounded by those two. So we're interested in this yellow region like that. And I'm going to make a geometric appeal. I hope this is believable. That's symmetric over the y-axis. Y'all kind of see that? Now, if you don't believe me, or if you require a little bit more persuasion, I'm going to first argue that we can write down exactly how it is that we will reflect over the y-axis. There's my y-axis. Reflection over the y-axis, we'll take a point x comma y, and the reflection over here like this, I can just kind of see from the picture, I'm reflecting over this vertical axis. The reflection basically is a horizontal movement. That means the y-coordinate's not going to change at all. The only thing that happens is the x-coordinate becomes the negative of what it had been. Right? So I claim this is a formula for that reflection. Y'all buy it? All right. Now, that being the case, I can take that reflection formula and I can plug this right into that formula. So I'm thinking about this green curve. I'm going to try to persuade you that this green curve actually is symmetric over the y-axis. Well, if I just plug in the reflection into this curve, you get the exact same curve. Right, so it's really easy algebra to do there, and seeing as we do now that you get the same curve when you reflect, that means this is a symmetric curve, and I think it's a pretty easy geometric appeal after that this yellow region, our domain, is also symmetric. Is that geometrically plausible? Yeah. Okay, yeah.
Yeah, since you have like x as the input, you just plug in negative x there.
So I didn't follow. I'm sorry.
Since we only have x as the input variable, you just plug in the negative x and it becomes positive.
It's easier than that. It's just that we're literally going to plug the reflection point into this equation and note that the equation doesn't change. The fact that x is an input here doesn't actually pertain.
Okay.
Is that cool?
Yeah, I'm just wondering about like the y there on the reflection.
Yeah, I did plug in the y. It's that, but nothing happens to the y. So effectively, I don't have to do anything. But I kind of, it's vacuous, right?
Okay.
I did even though I didn't have to do anything.
Okay.
Yeah, right. Okay, so we got a symmetric domain. Sweet. Now, what is not immediately obvious, and what you do have to do the algebra for, is you do have to establish that the integrand is odd. And how are we going to do that? Let's see, let me make a color decision here. How am I going to establish that the integrand is odd? Well, I'm going to have to compute f at the reflection. And I have to establish that I get a minus sign as a result. Right, now we'll go through this algebra. There's a tricky little bit in this algebra, but that's the big goal. Is I want to plug in the reflection and establish I get a minus sign. So here we go. How do I plug in the reflection? Well, I have a formula for my reflection right there. The reflection is negative x comma y, as we discussed, right? As we see from this picture right there. So now I'm going to plug that into my integrand. Now wait a second. What is my integrand? By the way, I'm going to go ahead and erase all of the geometry. This is just mucking things up at this point. So let me plug that in. Here's my integrand. This is what you might call, what I'm going to call f of x comma y. And here's the tricky bit. This thing that I'm plugging in here, I'm plugging in negative x comma y. The first input, negative x. I've got to plug in that first input, negative x, into the first input, which here is just called x. So what I kind of have to do is everywhere I see an x, I have to replace it with what I'm actually plugging in for that first input, namely minus x. Right? So the act of plugging this in turns that x into that minus x, and likewise for the rest of them. Everybody see that? All right, likewise for the y, but again, nothing happens. Everywhere I see my second input, I've got to put y, which is how I labeled my second input. So that's an easy one. Y just stays y. Okay, now having done that, it's kind of all over with the shouting and a little bit of algebra. But y'all are good at algebra. This turns into that. Yeah, question.
Should we be doing this with every single integral we're solving? Because I feel like it would suck up some time.
Of course, yeah. No, there are some earmarks to be on the lookout for. We'll talk about that as we go through future examples. But the short answer is I actually do. If somebody gives me an integral, one of the first things I do is I ask myself, hey, can I symmetry? I love symmetry. Maybe I can do that. But I know some little shortcuts to look for.
And should we be looking for even functions as well? Different zeros?
No.
Okay.
I am opposed to the even symmetry. There is a perfectly good theorem there. It is a valid theorem, and it allows for rewriting one question as another question. To me, it's a bad trade-off. You introduce risk that you'll misapply the theorem, which is actually very serious. And the benefit is that you still have to do a double integral, and it's basically just as hard as the other one. So I don't see in the risk and reward, it's like all risk, no reward. I don't see the point. Yeah, so I don't advise. Yeah. And that, by the way, that's why I'm not even going to present that theorem in class, because I don't want to give bad advice. Yeah, all right. Okay, all right, so let's see here. Reminder, we are trying to establish that this function is odd, so I need to know that when I reflect the input, I negate the output, and we've done the plugging in. It's just a little bit of algebra that remains that y'all are, of course, very good at, and this turns into that, which is literally the negative of what I started with. So this function is odd, and so I've got a symmetric domain and an odd integrand, and this integral is 0 by symmetry, and I didn't have to integrate anything, much less the monster that we were looking at. Everybody happy? This is a really powerful theorem. Really, really powerful. Okay, now let me talk about why I'm such a big fan. It's not that this, works sometimes. It's that this works shockingly often. Now, channeling my memories of being an undergrad many years ago, I took a lot of physics classes. Physics isn't that different from engineering. Y'all are going to be doing probably a comparable number of integrals to what I did in my undergrad days. And I did bazillions of integrals, right? So y'all have a lot of integrals to look forward to in your futures. My estimate, based on my memory of the experience, I feel like a conservative estimate is that 20% of the integrals that I computed were 0 by symmetry. That's a lot of integrals. 20% of a gazillion, right? So that's 200 bazillion, right? That's a lot of integrals. So super useful, super powerful theorem, and I don't get why so many books undersell this. Right, so our book, I think, has a couple of examples where they say, okay, by the way, here's a clever move, and they just kind of, it's an afterthought. I mean, to me, this should be a big deal, right? Which is why I make a big deal out of it in my notes, because you're going to see a lot of examples where this is the way to do the problem. So please be on the lookout for it, and I encourage you to use this method when it applies. That said, this being a class about ideas and reason. Oh, question. Yeah, question.
I have a question. What if your line of symmetry was like at an angle?
Yeah, I'll do one of those in a minute. Okay. Yep. Totally. In general, like if it's at some weird angle, it can be a little annoying to write down the reflection formula. And you can play some linear algebra games where, one way that you can reflect over an angled line is to reflect over the x-axis, and then rotate back. Right, so that does it. That would make the example arguably more trouble than it's worth, and we're not going to worry about it. We're going to have basically easy examples. Yeah. Okay, this is a class about reasoning, not answers. Right, so you do have to give me some reasoning. The reasoning has to be, I'm going to say, complete in the sense of you've got to cover all of the points of the argument that are relevant to what we do in this course, and here they are, in my opinion. So on my midterm exams, these are the 5 steps that you have to show me if you want full credit for making a symmetry argument. Fundamental to your argument is what line of symmetry are you claiming? It's a big deal, right? Sometimes a domain has multiple lines of symmetry. Which one are you using? If you claim that your function is odd over what line? Right? You got to tell me what the line is. I think it's very important. You're going to have the reflection to plug in to establish the oddness. So you got to write that down, right? Explicitly, what is your formula for your reflection? The fact that the function is odd, critical to the argument, right? That's what makes it work. That's one of the things anyway that makes it work. So please just doff the cap. Just acknowledge the importance of the fact that the function is odd by just writing that down, right? And it takes you 3 seconds, and this recognizes how important oddness is to the argument. Needless to say, you can't just claim it. You've got to also be correct, right? There's that. And by the way, for oddness, you also have to demonstrate. You got to. It's really not obvious to look at a function and establish that it is odd. It depends on which line of symmetry you're talking about. Plenty of functions are odd over some lines, but not other lines. So whether it is or isn't depends on these little details. So I want to see an algebraic demonstration of the oddness, just like we did here. Right? That is required for full credit. And then lastly, you also have to observe, and again, this is just a doff of the cap, it's really important the domain be symmetric for this argument to hold any water. So recognize that by saying, and the domain is symmetric. Now again, you have to be right? But I need that to get said. Okay, now you're going to notice conspicuously absent from this list, you don't have to demonstrate that the domain is symmetric. I gave you some argument about that up here, right? Domain is symmetric, and this was sort of a justification. This justification, I only did this in case maybe you weren't entirely clear in your mind and you needed to be persuaded. This is for your benefit, right? This is not something that you have to do. You just need to identify that the domain is symmetric and be right about it. And your geometric intuition is usually good enough for this, and I think that's fine for what we're doing in this course. Yeah?
Will you ever give us domains that are that kind of look symmetric but aren't actually? Or will it be very clear when we draw the geometry and we draw it correctly?
I'm not going to try to sneak one in on you, if that's what you want. No, I'm not into the trick question thing, right? But that said, I can't be responsible for what you might think looks symmetric but isn't, right? So I'll say it's never going to be my goal to do that, right? Yep. Okay, now, I also want to give you a warning, and this is a really serious warning. I mean, this is a real problem. I think symmetry arguments are dangerous. They're really quite dangerous. There is a serious risk, and by every time you make a symmetry argument, here's the risk you're taking. You're taking the risk that if, in fact, the argument doesn't work, if one little thing is wrong, if you thought that the function was odd, but it turns out it isn't actually, and you made an algebra mistake. If you thought the domain was symmetric through that plane, or through that line, but turns out it actually isn't, then everything kind of crashes and burns, right? The argument is a very delicate argument. Everything's got to line up. Everything's got to work, right? So here's the nasty reality then. If you try to make a symmetry argument, and if there is no actual valid symmetry argument, you've made progress toward a dead end, not progress toward a solution. Does everybody see the problem there, right? So we just can't give points for progress toward a dead end. In other words, that's not progress, right? So please do be really careful about this. If you're going to make a symmetry argument, which I encourage, which I want you to do, take some of this massive amount of time that you saved by using the symmetry argument instead of doing it by brute force methods. Invest just a little bit of that time savings in double checking. Make sure you've written down your reflection correctly. Just think it through, right? Make sure that your argument showing the oddness actually algebraically, just double check it. And take another careful look at your domain and just make sure that it actually has the symmetry that you're claiming that it has. Because, again, it's a little bit of a risky move every time you make a symmetry argument. Does that make sense to everybody? See another example. This is kind of a hypothetical exam question student response. Here's the question, compute this integral. Here's the hypothetical student response right here. And this student, you can see from what I've written over here, this student only got 2 of the 5 conditions actually checked. Now, it's tempting to look at this work and say, oh, well, yeah, but the domain is symmetric. The integrand is odd. What's wrong with that? Right? Well, the student has not given any indication of what they actually mean when they say the domain is symmetric. Symmetric through what line? Every domain is symmetric. Well, every domain is not symmetric through some lines, and some domains are symmetric through some lines, maybe only one line, but there's a lot of different things that this could mean. Symmetric by itself doesn't really say anything meaningful. Symmetric through what, right? So you got to tell me the what. You got to give me the line. And of course, you've also got to demonstrate that the function is odd. This student didn't demonstrate anything about the function being odd. By the way, this function is odd through some lines, but not other lines. Right? So if you're going to make this claim of oddness as part of a symmetry argument, it's very important that you establish that it's odd through the line you're using. Right? No argument. It's really not obvious that this is actually true. Right? And of course, if you are going to demonstrate the function's odd, you've got to have the formula for the reflection. So this student has skipped 3 of the 5, I think, really important parts of a full argument of claiming symmetry. And so the student gets 4 out of 10 on this one. Does everybody see the point there? Now the good news is I'm documenting exactly what the 5 requirements are, so just make sure you remember those 5 things that have to be included. You give me what I want, I'll give you what you want. Right? It's simple as that. Yes?
Is it actually 0 though? Like if you just students go through normal methods?
Yeah, if you were to do it by normal methods, yeah, you'd absolutely get 0 here. Yep. So not only is this integral 0, but the symmetry argument claiming that it's 0 does indeed work. Yeah, there is a full symmetry argument to be made here. The student just didn't really quite make it. Yeah. Okay. Yeah.
If we just solve this question like normally without continuing symmetry, would we still get like full?
It depends on the situation. Again, keep in mind, points don't come from answers. This isn't, of course, about answers. I know I say that a lot, right? But I say it a lot because it's important. So I'm looking for proficiency with ideas. An integral like this is actually pretty easy to do it by brute force. And so how much time do you really save by using a symmetry argument? It's not really clear. And an example like this, I think I'd probably just go ahead and give you full credit for that. That's fine, right? But if the integral is not nice, right? Or if symmetry is the point of the question, right? And sometimes I give little subtextual hints that, hey, there's a really good way to do this, right? I think it does show significant proficiency for a student to realize, ooh, there is an easy way to do this. And that shows more proficiency with the ideas, and more proficiency means more points. Yeah. And this isn't going to be dramatic, right? I mean, but it's going to be a little something. Yeah. Everybody good so far? Here's another example. The interesting thing about this example is how the reflection works. Somebody was asking me about how to find formulas for reflections. This is a nice example of that. But first, let's establish that this domain, what I have shaded in gray here, these curves being what they are, I'm going to make a geometric appeal that this domain is symmetric over the line y equals negative x. Now again, I assume that y'all are good with high school algebra and curve plotting and stuff like that. Make sure that you can plot those curves. Make sure that you can persuade yourself that this region bounded by those really does have this feature that you get the exact same thing when you flip it over this purple line. Right? And that's going to be mostly geometry. There's some discussion down here of why the domain is symmetric. Remember, you are not responsible for justifying the symmetry of the domain. All of this is just for your possible benefit in case you weren't quite sure you believe the result, right? All you have to do concerning the symmetry of the domain is document it and be correct. Is that cool? All right, so how do you do the reflection? This is the little tricky part here. It's tricky because if we look at some input point, right, if I think about how to reflect over that line, is not immediately clear how we're going to find the image of the, how we're going to find that image, that reflection point. It's not the negative, right? This is not reflecting through the origin, it's reflecting perpendicularly through the line. It's an important distinction, right? So I'm going to show you the method that I like. I think this makes the most sense. I'm open to other ideas, but whatever point you have there, x comma y, you want to reflect over that line right there. I like to think about what I call a rectangular frame. So think about that horizontal line representing the x coordinate and this vertical line representing the y coordinate. Right? And because these little green and blue line segments are, kind of right angles, right? They're horizontal and vertical, specifically. And because the line we're reflecting over is a 45-degree line, we get lucky. The reflection of that horizontal green line is this vertical green line. And the reflection of that vertical blue line is this horizontal blue line. And so then you can just kind of keep track of, okay, well, if the green line here, this x represents the x coordinate, well, this down here represents how far negative the y coordinate of my reflection point is, et cetera, et cetera. You just look at the geometry at this point, and it's pretty easy to persuade yourself that this reflected point here is negative y comma negative x. Everybody see that? So this is just an example. How you write down your reflection. Well, this is a useful tool when you're reflecting over 45-degree lines. If you're reflecting over an axis, it's usually pretty clear. One coordinate won't change. The other coordinate will get a minus sign, right? And there's an example on the homework. There is an exercise, I should say, on the homework where you're going to have to dream up another reflection. And I like to let students ponder and think about that one. If you can't figure it out, come to office hours. I'll be happy to show you. No big deal. Yes.
What if we're flipping over like x equals 2?
Yeah, that's the one that's going to be on the home, or something a lot like that. Yeah, absolutely. No, and so yeah, play with it. You write down the geometry and see if you can't just figure it out. And if you do, cool. And if you don't, come on into office hours. I'm very happy to just show you. Yeah. But I think there's something healthy about trying to figure it out for yourself. Yeah. Okay. All right. So again, now we've got to plug in the reflection. Let me see if I can get all of this onto the page here at the same time. Close. Okay. Well, let me just do. Okay. There we go. Okay. Here is my integrand that I'm fingers crossed hoping is going to end up being odd. Here's the reflection that I've got to plug into it. Again, keeping in mind this is f of x comma y. And let's think about what does it mean that my first input needs to be negative y. Right? It's a little weird, but if my first input needs to be negative y, it just means that wherever the first input is, I've got to put negative y there. Well, in this expression up here, my first input is called x. So everywhere up here that I see x, I'm going to put negative y, because negative y is what I'm putting in for my first input. So negative y then goes, let's see here. Negative y goes here and here, like so. Everybody follow that? It's a little weird, right? And by the way, if you're uncomfortable with the weirdness, another thing you can do is you can take your formula for your function and just rewrite it in terms of s and t, and then the confusion of variables disappears. There's no problem, and it's just literally plugging in. But very often people don't want to. It takes you an extra minute to write that down. if you're okay with this, I think this is an arguably more efficient way to do it. Likewise, negative x is my second input. I'm going to put negative x wherever the second input is. The second input here is y. So everywhere I see a y up here, I'm going to put negative x. And like that. And like that. Is that cool? Everybody with me? This is arguably the tricky part, right? So please do be very careful about this and make sure you plug in correctly. So again, at this point, it's all algebra. And y'all are experts with algebra, and you can rewrite that as that. And you'll notice that when you reflect the input as required, we negate the output. And this function is odd. We've already established a symmetric domain over the same line, integral 0 by symmetry. All right? Some of y'all might be thinking, you know what? That's more trouble than it's worth. I'm not afraid of polynomials. I'm just going to brute force through this. Don't forget your domain. You're going to hit corners. This is actually 3 separate iterated integrals, some of the bounds of which are reciprocals. So it's actually significantly uglier than it looks. And this is quite a bit easier of a solution. Everybody on board? All right. All right, another example. This is a landmine example. I show you this so that you can have this experience in the lecture instead of on the exam. I don't want anybody to have this experience on the exam, right? This is a dangerous problem. Lots of students will see something like this on an exam and get tempted by the seeming lure of a symmetry argument. That does not work. And the devil's in the details here. So let's draw what our domain looks like, and let's think through the details. Let's see, our domain has corners at 0, 2, negative 1, 0, 1, 0. Our triangle is what's got those as its corners. Something like that. So there's our domain. Our domain is this, and then here's the mistake that a lot of students will make. A lot of students will make the mistake. Oh, symmetry, symmetric domain, odd integrand. What could be more clear? It's obviously an odd integrand. It's an odd power. Symmetric domain, odd integrand. A lot of students will say integral 0 by symmetry. Walk away, turn the page, convinced they just scored. Right? It doesn't work. It just doesn't. There is no symmetry argument. It's not that this symmetry argument leaves something to be desired. It's that there is no symmetry argument to be made here at all. And any attempts to make a symmetry argument are just moving in the wrong direction toward a dead end. Right? No symmetry argument at all. And the reason it's subtle, right? But you can see here in what I've already drawn that the domain is symmetric through the y-axis. And by the way, only the y-axis. There is no other symmetry for this domain. The y-axis is the only symmetry for that domain. Whereas the, let's see here, the integrand is odd if I stick a minus sign on the y-coordinate. If you stick a minus sign on the y-coordinate, your reflection looks like that, which means that the symmetry of the integrand is only over the x-axis. And symmetry arguments only work if you use the same line for both of the symmetries. This doesn't. Crash and burn. There's nothing there. This is a dead end. There is no symmetry argument. By the way, here's another tip-off that you know that there is no symmetry argument to be made here. You look at this integral. The integrand is y cubed. Let's look at our domain. Y is always positive. Y is never negative. That means y cubed is never negative. There can't be any cancellation if the integrand is never negative. Right? So, not possible. Yeah?
So, could you please repeat this part of, like, looking at the, okay, I get that the symmetry on the y-axis.
Yeah.
But then looking at the integrand of the x-axis.
Yeah, well, so, I mean, think about how, I mean, to some extent, I'm going to have to say you got to work it out, but the intuition is that where the necessary minus sign would come, if I want to claim oddness here, is I would need to have a minus sign on the y-coordinate. Well, that's what this would look like. If you reflect and get a minus sign on the y-coordinate, then this is what your reflection looks like, which means the reflection's over the x-axis. Yeah, that's right. That's right. Yeah, okay.
If the triangle was different from the origin, would that then be possible?
You could ask me after class, but I don't have time to go to hypotheticals. Yeah. So maybe it's going to be a lot of details we got to write down there. Yeah. Okay. So always be careful. Watch out for these landmines. Again, don't think of it as I'm going to do it to you on purpose. Think of it as that life is going to do it to you. And you can speculate on whether that's on purpose. That's philosophical. Okay, real quick, I want to point out there's a three-dimensional version of it. It's exactly what you would think. In 3 dimensions, we don't reflect through lines. We reflect through planes every morning when you wake up and look in the mirror. Right? You're reflecting through it. The mirror is the plane, and your reflection is like that in the picture here. Right? So notice we make the morally equivalent definition of oddness. Reflected input negates the output. Again, a symmetric domain is exactly what you think it is. It is its own mirror image. You don't need to worry about the formalities of how we write that down. And we get the same theorem, morally equivalent theorem, that if you have an odd integrand and a symmetric domain, then the integral is 0, with the warning that both conditions have to apply, and it's got to be the same plane for both symmetries. So it's morally equivalent. It's practically the exact same theorem. And let me just get this one example done here. Horrible integral. Now again, the integrand doesn't look that bad. But don't forget the domain's a ball. That means there's square roots all over the place in the bounds. Right? So that's not pretty. You could say, hey, clever, let's use spherical coordinates. Sure, you could do that. Now you've got a lot of trig. And again, not that it can't be done, but it's gonna be an annoying integral, and there's a fair amount of this. You don't really want to have to deal with that. Here's the beautiful argument. Let's think about the xy plane. Right? Now, geometric appeal, the xy plane is like this. Reflecting through the xy plane would simply introduce a minus sign on the z coordinate, like so. Balls are clearly symmetric through any plane that contains the origin. It's just, gotta love it. And because we get this minus sign in our reflection, specifically we get a minus sign on the z coordinate. We get a -1 cubed. That is -1. That is the minus sign that we need. This integral is 0 by symmetry. That's pretty sweet. Everybody good? Okay. All right, we're out of time, I'm sure. So see y'all later. Have a good one. Yeah, so we made it. We finished 5.5. 5.5 is fair game for the exam, and I'll update the lecture schedule.
But not Wednesday.
Correct. Yeah, today is the last day. Okay, real quick, let me do attendance. Don't forget about attendance, please.